Hi, my name is Ant Joju, and this is a video demonstration for our assignment 3 of machine learning course. So, in this, we have two parts, part A and B, and on part A, we're dealing with the image convolutions. So, let's jump in and start working on it as I'll go through the video. So, first of all, we're importing all the necessary libraries and getting the image that we need to visualize. Then first of all, let's see the image, how it looks like. So this is a car image of a car, and um, then we compare the values of color channel 0 and 1, and we get it as false. And the next, say the color channel surrounding input are variable and printed. So now we see the image is different now. Um, so we are now going to visualize a value inside the resulting array, which we stored earlier. So now we got a different image. So then the next one is a convolution with the 2D kernels. So so we're creating a pattern array by adding two rows and columns at the beginning of each section, and then we're gonna see the uh, apply kernel to the array values. So once that's been added, we're gonna see the image. So you could see the kernel values on the side. Then we're gonna do the standard convolution. So we're gonna trim the function with the values from 0 to 255. Um, and so then we're gonna define the function for the 2D kernel. So then line detection. So we had to detect the line. So we create a horizontal kernel and translational kernel. Then we're gonna see if we plot the image, we're gonna see the lines of the image. Um, so the next one is based on the kernel represent the above image, create a kernel to integrate 45-degree lines using convolution. So here we're gonna do the diagonal kernel and create an array for then plotting that image. Um, then based on we create a kernel at 135-degree using the convolution. So now we're gonna check for the 135-degree lines. So for that, we're gonna see that. So you could see the difference between the images as we go through. Then edge detection. So we're gonna detect the edge of the image. Here you can see edges of the image. Then this is the second image using edge kernel 2. So we're gonna see much more plotted edge on the second image. Then next up here you could see another image with a much more defined edges. Then we're gonna go to the part B. For part B, so we're gonna import in the libraries. Then load the data set. Then we're gonna do the one hot encoding to the target values and building thing. Then we gotta build the neural network model. So we're using five layers, convolution two-dimensional, max pooling, flattened, dense layer. One is using ReLU and one is using softmax. Then we know our optimizer is Atom optimizer, and we're gonna show the summary of the model. So this is how our model summary gonna be like. Then so we're gonna create a custom callback function during the training as well. So we're gonna do that. Then the training the network. So we're gonna train the model using 50 epochs. So it's gonna take a while. So you could see as we go through the values, you could see the changes in the rescheduled training and also reached value. So you could see the notice. We're gonna plot it afterwards. So once we plot, we could see the changes in the training accuracy and validation accuracy in the curve. So you could see as it gets more to 20, it's going to get flattened up here. It's going to increase at the beginning, then it's going to flatten. So we had three questions. So did the network present the signs of overfitting? So yes, so the network shows the signs of overfitting. Approximately after 15, it sees the validation accuracy almost flattens or plateaus down there. Uh, write down how many layers has and their type. So we had five layers as we talked. Yeah, a convolution layer, convolution 2D or max pooling 2D, flatten, dense layer with the radial and dense layer with the softmax. And briefly explain the purpose of each of these layers. So the conversion 2D extracts spatial features using the kernels. Max pooling 2D reduces spatial dimensions, retains only important features, and flatten the layer which use convert 2D data to the 1D dense layers. And dense layers value learns the non-linear combinations of the features, and dense softmax outputs the class probabilities. And we had the next question is to one more convention layer, more rent again. So here we adding one more convention layer after the max boolean duty appear. So after that, when you run it, we're gonna see the changes in the train and the reach value. And once you plot it up, we're gonna see the difference. So it started getting validation accuracy much earlier, and you see the difference between training accuracy and validation accuracy appear. And then the next question is add a dropout layer and compare just to the previous one. So here we're gonna add one more dropout layer up here and um, uh, uh, to the model, and we just gonna run it through again. Then we would see the difference in the values, but let's go for the graph so we could do the different. So here, up here, you see the greater difference between the training accuracy and validation accuracy as it console is more closer. So, so the next question is explain the uh, like what is the purpose of dropout layer, how it works, and briefly explain your video in your own way. So, the dropout layer randomly deactivates neurons during the training to prevent overreliance for specific roles nodes. So this reduces overfitting and by increased redundancy in the learn features. So that's what we try to do with the dropout layer in this last model. So that's it for my video. Thank you for watching.